So we went over, so I showed you a couple problems on Monday, right? That might be examples of what a problem what kind of problems you'd get on an exam or on the timed lab tomorrow. So here I'll go over a couple then, and I'm going to start. What we're going to do is I'm going to focus on these two problems over here. I'm going to solve them for you, and then you're going to use that to see if you can't figure out this one by yourself. There should be no reason, by the way, when you're working on this is not going to be for credit. This is mainly to show you, to see if you can't come up with a solution on your own. It shouldn't take more than 5 or 7 minutes, and it's more to see how a self-check to see how ready you are for the timed lab tomorrow. Okay. And so the questions you'll get tomorrow, they're going to be of the vein of, given a tree of stuff, like a tree of strings or a tree of integers, do something with that tree of stuff, right? Now, here's one that I came up with yesterday that I think that I would totally ask on, that would be something I would totally ask on an exam-like situation, which is, and so let me define what I go over here, which is, given a tree that's composed of strings, right? Here's a tree that's composed of strings. I want you to count not how many strings there are in there, but how many characters there are, right, in the entire tree. So I just want to reiterate, right? If I was asking for the number of strings, that would be fairly straightforward. You would just return the size, right? Done. But so I'm not asking that. What I'm asking for is, right, if the tree is made up of cat, dog, moo, you would return 9 because you'd have 3 characters for cat, 3 characters for dog, 3 characters for moo. All right, that makes sense for everybody. So there's 2 types of algorithms, and almost always on the exam, on timed labs, and on the final exams, we almost always ask a problem that will be solved with the traversal algorithm, not with the zigzag algorithm, which is what you use for contains or for add. Instead, what we like to do, and then the other thing we like to do is give you something that basically can be broken down using the simple algorithm. So if you know recursion, you can solve it in somewhere between 7 lines if you're doing things like just one statement at a time, or if you decide to group a bunch of operations together, you can do it in 4 lines about. And as long as you know how to use recursion, it's super easy. If for some reason you have forgotten how to use recursion, there is one solution. There is one easy solution for you, and that is to use a stack and to push and pop, right? Thereby simulating recursion by pushing and popping, or perhaps recursion simulates a stack. It's a chicken or egg problem there. The other type of problem that you might get is a traversal algorithm that goes level order, and that can't be solved using one of the traversal, like pre-order, in-order, post-order traversal. You're not going to get that tomorrow, by the way. That doesn't generally come up because the way we cover that in chapter 10, but the way you do a level order traversal, where you start at the root and then you do the root's children and then you do the root's children's children, rather than, so you start from the top going left to right, like you would if you were reading off the array, that representation of a binary of a heap. If you did that, you use a queue for that. And it's a breadth first search, which we learn in chapter 10, and that's the other type of thing. And once you identify that case, it's actually, again, very easy to solve. So let's go ahead and get into this. So I want to figure out the number of characters that are in this tree. So root, remember here, when I'm taking in root as a variable over here, that means not necessarily the root of the tree over here, but it's the root of the tree or the subtree, right? It's a recursive data structure. And so all my decisions are made locally, right? We're being very, the beauty of recursion is that you make local decisions. You figure out where I am now. So first things first, we need a base case. Now in these cases, in traversal algorithms, the base case is almost always, and that's just simply so I'm hedging myself there. I could pretty much say always, but I'm pretty sure there's a case where it's not, but it's almost always, is the root null? Is the thing I'm currently at null? if root is null, right? So let's think about that. If the root is null, that means the tree I have is empty, or the subtree I have is empty. So how many characters are in it? How many characters are in an empty tree?
0.
0, yes. Return 0. That's your base case right there, right? Pretty straightforward. All right, so now I have to figure out, all right, I've got this tree over here and it has some word in it. Then I have some subtree over here to the left, and I have some subtree over here to the right, which may or may not be empty, but if they are empty, guess what? Then it will return 0, so that's not a big deal. So I have to calculate basically 3 things. I have to calculate the size of my left subtree, calculate the size of my right subtree, how many characters in my left subtree, how many characters are in my right subtree, and how many characters I have. So of those, calculating how many characters I have is probably the easiest, right? This is a local decision. So int num cars in root. So how many characters how would I find that out? How many characters are in the root node? So first I have to get the string inside the root node, right? So that's root.item. And then so the item's a string, so how do I figure out how many characters are in it? Dot length. Okay, that's pretty straightforward there. All right, now I have to figure out, let's see, int num cars in, let's go with my left side. How many characters are in my left subtree? I don't know, that's a hard problem, so we use recursion to figure that out, right? So what can I do to figure that out? Number of characters, what? Yeah. Root.left. All right, same deal. How many? If I want to figure out how many characters are in my right subtree, I ask root.right. Right? Number of characters in the right subtree. And if they're empty, no worry, they're going to return 0. All right. So now I've got my answer. So what's my answer? Anyone? Just shout out. It's the sum of those 3. Num cars in left. So let's do this in order. Num cars in root plus num cars in left plus num cars in right. And that's the answer to this one. Now, as you can see, it didn't require too much thought or effort, right? It was just simply, am I an empty case? Otherwise, I went with a pre-order traversal here, but it could have easily been a but it could have easily have been a post-order traversal or an in-order traversal, right? Because when we add things together, it doesn't matter what order it comes in, right? So we're good there. So, and these recursive calls just simply figure out the number of, figure out my left subtree, figure out my right subtree, process my left, process my right, process myself. That makes sense to everybody? All right. So occasionally, now on the practice exam, I have a tendency to give out something a bit harder, but the same principle holds. So this is figuring out are two trees equal to one another, okay? Right? Telling if 2 trees were equal to one another, right? So basically, there's kind of 4 broad possibilities in this case, 4 cases, right? Over here, our base case was if our root is equal to null, right? And so that means we have to consider 2 possibilities for each of these tree A's and tree B's. Now, the equals method, basically, it's asking, are the trees equal? Does that mean, in other words, do they have not only the same contents, but also the same shape, right? Do they present the exact same data in the exact same way? Do they have the same shape? So there's 4 possibilities here. Tree A and tree B are both null, right? One is null, the other is not. One is null, the other is not. And then the 4th possibility is they both have data, right? They both have something there. So let's think about this. Let's just enumerate those 4 possibilities. So if tree A equals null. And I'm going to put that first because that most closely resembles this base case. And tree B equals null. And again, these are just the roots of the trees, or they are trees or subtrees. Okay. So I'll go ahead and program that out. So I use copy and paste there so I can go through the other possibilities. So let's say we have something for tree A, but tree B is null. Or maybe tree A is null and we have something for tree B. And then our else condition is, well, the only other possibility, which is that tree A and tree B are both a node. So here we have three base cases, so to speak, right? Case number one, if they're both null, are they equal? Yeah. So return true. How about what if one is null but the other is not? Definitely not equal in that case, right? Return false, right, for both of these things. And I'm enumerating them out in this way, and I'll go ahead and add else ifs to be super explicit about it. I'm enumerating them out in this way just so that it's easier to parse for us. All right, otherwise now there's something in both of them, right? So now I have to make that kind of local decision, right? I've got essentially, so our possibilities were, right, on the board we had nothing here, right? Then we had the possibility that A had something but B had nothing, so they're not equal. We had the possibility B had something but A had nothing, so they're not equal. And now we have this possibility of, we have tree A, which has its subtrees, possibly, we don't know yet, and B has its subtrees, right? So now we know we're in this situation where we have A and B. So the question is, the first thing we have to ask ourselves is basically the easiest thing we can determine locally. Are A and B equal to each other, right? Do they have do the nodes A and B have the same things? So if tree A dot item dot equals tree B dot item, so if their items are equal, we'll figure that out, okay? But if they're not equal, that's actually pretty easy for us to figure out, right? If they're not, if the contents of those two nodes don't equal each other, right, then the trees aren't equal. So I'll go ahead and return false there. So let's go. So now we find out, we compare A and B, and it turns out, oh, it's not an easy thing. They both match. Then we have to do some recursion here. So the question for them to be equal now is that if the roots are equal, then we have to confirm that both the left sides are equal and the right sides are equal. Okay? And if the left sides and the right sides are equal, then they're equal. Okay? Right? If one side is equal but the other is not, then they're obviously not equal. Right? Everybody following this so far? Okay. So let's go ahead and create more variables. Boolean left side is equal to, well, the only thing we can figure out to do that is with recursion. So we'll do equals tree A dot left and tree B dot left. Right? So we'll figure out so this will return, is the left side equal is A's left side equal to B's left side? Now we can do Boolean right side is equal to the right sides being equal. And then we would return, okay, oh yeah, I should make that lowercase, left side and right side. Right? And we don't have to check the center because we already did that, right? We already checked, are the roots equal? So we have to just confirm, are the left sides equal and the right sides equal? So this one's definitely harder than anything I would ask on an exam because it's got a bit more to it than I would normally ask. Generally, you rarely see something where you have to compare two trees to each other. I like that, but it's an interesting question because it follows the same kind of pattern, and each of the once you break it down into the individual cases, it actually becomes quite trivial. Most of the questions resemble something like this, and where we take the number of where we given like something like this, we compute the values on the left and the right and add them all together. We can actually shorten this up quite considerably. I mentioned we can get these things down to 4 lines, and this is how. Well, we just simply say the return statement instead becomes, well, we got to add what's in the root plus the number in the left, so number of cars root dot left plus the number of characters in root dot right. All right. Oops, sorry, moved a bit too quickly there. But everybody see how that's now a 4-line solution to that problem? Albeit one long line, but a legit 4-line solution. All right. So now what we'll work on today, this isn't for credit or anything, this is more of a self-check, right? Let's see how you can apply what you've learned. So what I want you to do, and I would say if it would be more worthwhile to boot up like something like Notepad rather than an IDE for doing this, just so you can do it quickly. Given a tree that's made up of integers, right? I want you to compute the sum of all the numbers in the tree, right? So if I've stored 1, 2, 3, 4, 5 in the tree, then the answer would be 1 plus 2 plus 3 plus 4 plus 5, right? Which would be 15, I believe. So all right, so take 5 minutes and see what you can come up with. And again, it shouldn't be that hard of a solution for you guys.